All right, welcome everybody to today's webinar by the IEA SHC Solar Academy and hosted by the International Solar Energy Society, ISIS. We are very pleased to have all of you here. My name is Arabella. I am the Congress's Communications and Outreach Officer here at the ISIS HQ in Freiburg, Germany, and I will give you a short introduction into ISIS and the work we do, as we have many new participants joining us on the webinar today. The International Solar Energy Society, ISIS, is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISIS represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. And ISIS works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISIS, and you can always find more on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings. ISIS members can also get discounts and even free registration to ISIS events and partner events. Every month, ISIS publishes a newsletter for our members where you can follow our progress and share your news. And members can also subscribe to our academic journal Solar Energy, our flagship publication, at a reduced price. So we welcome those who are not yet a member to join us today to support our work. For those who are already a member, we thank you for your support. And as a special benefit to all attendees of today's webinar, we are very happy to offer a special discount when signing up as an ISIS member. All attendees of this webinar will receive a 20% discount code as a follow-up over the coming days. Now, before we get into the webinar itself, a quick note on the Q&A session. We're going to have a Q&A session at the very end of the webinar after we have heard all of the presentations. And you can use your chat box to send in your questions at any time throughout the webinar. When you send in your question, keep them short, keep them precise, and ideally indicate who they are for so that our moderator can then easily assign them to any of the speakers. And now, with that, it's my pleasure to introduce you to our moderator for today, Bärbel Epp. Bärbel is the founder and managing director of the German consultancy Solrico, Solar Market Research and International Communication. She is responsible for the international newsletter on the portal Solar Thermal World and reporting exclusively about market and technology trends in the solar heating and cooling sector. And since many years, Bärbel has been the co-author of the SHC chapter of the annual Global Status Report by REN 21. Now, I'm happy to hand over to Bärbel. Bärbel, thank you for joining us, and the floor is yours.
Thank you very much, Arabella. Good day, good morning, good afternoon, wherever you are in the world. I'm happy to welcome you to this new webinar today in the series of Solar Academy webinars of IEA SHC. And I will shortly introduce you what is the IEA Solar Heating and Cooling Technology Collaboration Program, a long name. It's a project-focused international R&D collaboration, quite old, 1977 founded. It has 19 member countries, the EC, and 8 international organizations. So you see that we cover all the colored countries on this map are members, and there are around 300 experts all around the world, partly from research, partly from industry, that group and work on solar thermal specific topics. And the topics they work on, we have listed here for you. They are currently 7 tasks, how we call these projects internally running. They are on industrial solar heat, efficient solar district heating, compact thermal energy storages, solar energy buildings, solar cooling for Sunbelt region, and solar neighborhoods. This is the one we have today. What can the Solar Academy offer you? Well, with these webinars, which we hold regularly by ISIS, mostly quarterly, our next webinar is planned for March 22nd, 24th on global certification. And you find always the announcements either on the ISIS website or on the IEA SHC Solar Academy website. Also, you can look into a lot of videos that we have done with experts on past Academy webinars or conferences. And the Solar Academy offers on-site trainings. They are organized and held by the IEA SHC experts upon request of the member countries. And the past trainings have been as far-reaching as Caribbean, China, South Africa, and UK. Where to find more information? Certainly on the website. On the website, also each of these project areas have its own sub-web page. We have social media activities where you are happy to join. We have this YouTube channel I mentioned already, and if you have additional questions, you can contact the Secretariat of the IEA SHC program. So today we have an interesting group of researchers working on solar neighborhood planning. This task is called 63, so they are numbered by starting point. It's a 4 years project, so the researchers of this group are now halfway through their project, so they show us intermediate research results. And yeah, I think we will start straight away to introducing you the first of our speakers. So Maria Wall, she will hold the first speech, and she is Associated Professor at the Division of Energy and Building Design in Lund University in Sweden. She is Project Manager of Task 63 on solar neighborhood planning. And she has long-term experience in, organizing these big research groups, networks, as she was also chairing the previous task on solar energy in urban planning. So Maria Wall will give us a short introduction in what this whole task 63 is working about. So Maria, I'm looking forward to your speech.
Thank you, Bärbel. Let's see. So I hope you can see my screen.
Yes, perfect.
So I will give a brief overview of the project Solar Neighborhood Planning, and that you will hear more about today. And first I would like to kind of highlight what we can use solar energy for, all the benefits, all the good things with solar energy. I mean, we can use it for passive solar energy, both indoors and outdoors, to reduce heating demand and improve thermal comfort and health. We can also use it for daylighting buildings and outdoor areas to reduce electricity for lighting and to improve visual comfort and health. And we can use it for local renewable energy production using PV and solar thermal systems. And in this way, we can create energy or resource self-sufficient environments. So we don't need to rely on energy imports. And in this way, we can create resilience to energy price fluctuations. And we can use it for local food production and green areas to improve air quality and reducing stormwater. So we can really use it for a lot of things. But I think that we need to use it more efficient and more wisely in the future. I think we can improve this a lot. So the opportunities, examples of that for solar neighborhoods is that it is a means to achieve net zero energy districts and low carbon cities. And if we address both solar energy production and passive strategies when we plan neighborhoods, this enables us to identify synergies and to avoid conflicts between competing uses. So we shouldn't waste the possibilities to use available surfaces in neighborhoods. And we need to create long-term solar access. This is very important. So if, for instance, if you have a building, if you have a house where you put solar panels on the roof, you don't want your neighbor to erect a building on the other side of the street just 1 year after and destroying your solar gains and your investment. So you need really to have this secure access to solar access for a long time. And this is something we need to be better on when planning cities. Going to the project specifically, we started in 2019, and the project ends in 2023, the end of the year. And so we are midways now, and the objective is to support key players to achieve solar neighborhoods that really facilitate this long-term solar access with a good planning. And we work with and on new neighborhood development and to improve existing neighborhoods as well. And we deal with both active solar strategies and passive solar strategies. And we define a neighborhood as a group of buildings within a specific geographic area, often including different types of buildings and functions, open space and infrastructure. And the neighborhood can be part of a large city or an isolated community or something in between. So, and of course it can be connected to a district heating or cooling network or outside such. And this gives different boundary conditions that we have to take into account when planning. We organize ourselves in different subtasks and with different leaderships. And we have 4 subtasks. A, on solar planning strategies and concepts with a Canadian leadership. B, on economic strategies and stakeholder engagement with the Italian leadership. Subtask C, on solar planning tools with a joint leadership between Sweden and France. And subtask D, on case studies, which is jointly led by all the leaders, and we also have a coordinator helping us from Norway. And the case studies are really strongly connected to the other subtasks and topics where we work together with and collaborate with municipalities and the key stakeholders. And I am the general project leader. And the names here in red are the ones that you will meet today in the webinar. And the participating countries in our project are mainly some European countries, but also Australia, Canada, and China. So in total, we are 9 countries working on this. And with this, I stop my very brief introduction. Thank you for listening.
Thank you, Maria. Well, I think you really showed us how complex this issue is, solar neighborhood planning, and how surfaces are an important but limited resource in cities that aim to become climate neutral. I think this was a good introduction and an overview. So our next speaker, Caroline, I think Maria already introduced her as subtask A leader. She is from Canada, and because of the time zone, she cannot join us personally, but we will record her speech. She is an associated professor at the University of Calgary in Canada. Her research is focused on the impact of building shapes for solar potential and the development of multinational facades, among other subjects. Her research is very multidisciplinary. It brings together building engineering, architectural, and urban design. And she is, as Maria mentioned, the chair of this subgroup, which is called Subgroup A, and it's titled Developing Strategies for Net Zero Energy Solar Communities. So we will listen to her speech. Arabella, it's your turn.
Good morning. My name is Caroline Hashim-Bermet. I am Associate Professor at the School of Architecture, Planning and Landscape at the University of Calgary in Canada. I'm also a leader of Subtask A, Solar Planning Strategies and Concept within the IEA Task 63, Planning Solar Neighborhoods. I'll be talking today about some strategies and concepts for planning solar neighborhoods as part of the efforts and work that's done within Subtask A. Starting with a little bit of context, solar neighborhood planning is becoming significantly important as part of the efforts to reduce the environmental impact of increased urbanization, where by 2050 we are expecting that 70% or more of the world population to be residing in urban areas. Solar neighborhood relies on a holistic and integrated design approach that spans from the building components and building level to the urban level. Within this holistic approach, buildings and surrounding areas, including public spaces, landscape, streets, and street furniture, should be considered as active elements of the energy network rather than standalone energy consuming components of the grid. So at the building level, solar building design relies on passive designs in buildings. In fact, passive design is often attached to solar building designs. Improving solar access together with various design principles such as thermal mass, high insulation, airtight envelope are some of the basic principles of passive solar buildings. These principles can be implemented in all types of buildings, including residential buildings, including offices, institutional buildings, and others. Daylighting, passive heating of perimeter zones, passive and hybrid ventilation, coupling ventilation with solar chimneys, as we can see in some of these sketches, can significantly affect energy demand, reducing the energy consumption of buildings and their dependence on the local grid, which also can increase the resilience of buildings for climate shocks, and climate risks. Solar building design allows to improve energy efficiency of buildings, designing building shape, layout, and building envelope to maximize solar access and utilization within the building, affect the energy consumption of these buildings. It also allows better designed solar energy generation, since well-designed building envelope can be exploited to integrate solar technologies such as photovoltaic systems, such as thermal collectors or hybrid photovoltaic thermal systems for the generation of electric and thermal energy. Talking a little bit about building envelope design and the integration of technology. In fact, building envelope can be optimized to maximize the surface area and the exposure to solar radiation while presenting architectural and aesthetic flexibility. These are some examples of a theoretical study that was done by myself and my group at the Solar Lab at the University of Calgary, where we try to optimize the building envelope shape geometry through a different design of folded plates that allows maximizing solar radiation on these plates. This also, we were integrating different type of photovoltaic system in different colors. At the level of neighborhood, many aspects affect an optimal solar planning. For example, the type of neighborhoods the building mix presents can affect the building designs and as such available surfaces for solar technologies. Also, the ratio of mix of commercial to residential buildings, for example, within a specific neighborhood type is important, especially when the goal is to achieve a net zero energy status. An optimal ratio of commercial land area to overall built land area can be between 23% and 32%. This is according to a theoretical study that we conducted, where according to this ratio, we were able to integrate enough photovoltaic panels to allow achieving net zero energy within a mixed neighborhood. Density is another important and critical factor in the design of solar community. Studies associate, in fact, increased build density with sustainable development, but this should consider cumulative effects of various additional factors of a compact development. For example, the land use, the transit accessibility, job availability within walkable distance, walkability, and others. There are other important elements in the design of a neighborhood that also impact their solar access and solar potential and their design as solar neighborhoods. This include green and spatial areas. Landscape can offer, in fact, solutions for the integration of photovoltaic panels as well as solar thermal collectors and allows really to generate more energy that can be utilized in these neighborhoods. Orientation of streets can affect the potential to capture and utilize passive solar energy as well as energy output of various solar technologies. And as such, they really should be considered from early design stage and the building around them, they should be designed to get the best performance with the best orientation. Now, talking a little bit more in details about the work that is currently ongoing in subtask A, we developed specific designs of archetypes to study solar strategies. Archetypes in this task are considered as representative neighborhoods that of existing or new patterns in different countries. This include repetitive patterns of commonly applied design, such as that include streets, building types, shapes, density, etc. And here is an example of well or commonly seen neighborhoods in North America, residential neighborhoods where we see a grid layout together with the attached and detached houses. Other examples of archetypes can be representing uncommon or innovative examples. We have a few of these that were also presented and proposed by the experts in subtask A, such as, for example, in Sinfonia in Bolzano, the campus in Norway, and so on. Other archetypes can be theoretical cases presented in literature or especially developed to study different strategies. And here are some also example of theoretical neighborhood, and I'll be talking a little bit about these and some examples of the results that we obtained in a couple of slides. A methodology is developed also to collect information about these archetypes, including building types, materials that are employed in buildings and building envelope, outdoor areas, and also materials employed in these outdoor areas, streets, etc. These information are collected in a matrix or what we call matrix. And this is a Excel form that can facilitate their input into various simulation tools, allowing us urban level simulations. Once the base neighborhood of each of the archetype is established, various solar strategies can be then analyzed. Here now I'm presenting some of the theoretical examples that I just mentioned of a neighborhoods, what we call the neighborhood units, and these are small neighborhoods designed according to various sustainable measures and range from residential dominated neighborhoods to higher density neighborhoods with commercial centers that include different type of trades and different type of buildings. The study aimed here at analyzing various renewable energy and role of solar energy for thermal and electrical production. I want to highlight also that the PV were accommodated in roofs and some portion of the facades when available. That's mean when we have higher high-rise buildings, and STC or solar thermal collectors are accommodated in parts of the roofs when PV area allows for this, and in landscape areas. Results of this study shows that PV electricity plays an important role in fulfilling significant portion of the total electricity need of all the neighborhoods, especially up to 95%, in fact, for a small scale or less dense neighborhoods. Some neighborhoods with high density and high amount of commercial building needs additional land area to accommodate PV panels that fulfill all the electrical load. And this can be quite significant, about 80% to 85% as compared to the total land of the neighborhood. Some of the high density neighborhood as well require significant additional area also of landscape to accommodate the solar thermal collectors to fulfill the thermal requirement. In this example, some of the small neighborhood units that I showed before were combined together to, according to their electrical energy performance, to allow achieving net zero electrical energy. And in this case also, PV plays a significant role in achieving net zero electricity status. In all these neighborhood combination, the major portion of the PV electricity is supplied by roof-mounted PV systems. Also, the study shows that the on-site sources can supply between 19% and 45% of the thermal requirement for the neighborhood combinations, but we still need additional solar thermal collectors, especially in high-density neighborhoods and larger neighborhoods. This landscape area that's required to install these solar thermal collectors is significantly lower than the examples that I showed before for the smaller neighborhoods. The landscape area can be about 15% of the total land of the neighborhood, which can be, again, as mentioned, much lower than examples before, but also more feasible from urban planning point of view. Now, coming to the design of solar strategies and their analysis, different solar strategies will be analyzed using the archetypes that kind of presented, or the archetype concepts that I just talked about. This include, but not limited to, integrated solar technologies in roofs and facades, landscape integrated solar systems that can range from very traditional standalone elements to more interesting and kind of a more designed. A workflow is developed to implement and analyze solar strategies, taking into account various factors such as spatial design of the neighborhood, the optimal surface areas to integrate technologies, neighborhood operation, and interaction with the local energy system, both electrical and thermal systems. Coming to the deliverable of subtask A, there are a number of deliverables, but I want to highlight the most important. Two summer schools or fall schools are designed. One of them, a fall school, is already conducted in September, October of this year. And it was attended by about 14 PhD students from 6 countries that were trained in complex urban level simulations. Instructors from 9 different institutions were involved in the training. The next summer school will be conducted next year, hopefully in person in Calgary. The final deliverable of the subtask A, and which is still under development, the results and the analysis are conducted to get to this stage, will consist on a web-based database that present various solar strategies and their potential application in example of neighborhoods under different climate. These neighborhoods can be, or solar technology can be selected according to the type of the neighborhood, the available archetypes that were studied, and available results will be shown to give an example of how to apply these solar strategies and what's their impact. This can offer flexibility of design for planners, architects, developers, and other key stakeholders by presenting examples of potential solar solution for different settings. And with this, I would like to thank you for attending this webinar. And if you have any question, please direct these questions to the organization of the webinar, and I will be happy to answer them as soon as possible. Thank you.
Yeah, well, this was an interesting insight. I think we understood a lot about what case studies play, how important they are to understand the planning, the process, the tool usage when doing this complex neighborhood planning. So we will see how questions to Caroline can be also tackled by the other speakers. Otherwise, we will gather them as Caroline suggested. And also, I want to apologize for any inconvenience you had while regarding this video. It seems that some of our participants had either with audio or with video problems. So I hope that most of you were able to see it, and the recording will be for sure available at the ISIS website some days after the webinar, so you can listen to it in peace then one day. Okay, so we come to the next speaker. From Italy. It's Silvia Croce. She is postdoc researcher at the Institute of Renewable Energy called EUREC Research in Italy. Her research work aims at gaining insights into solutions for an integrated design of urban build and natural environment with a focus on outdoor climates, thermal comfort, energy savings, and renewable energy production. She's a building engineer, architect by training, and holds a PhD in engineering. So you see that this working group of Maria Wall is really a very interdisciplinary one. The participating experts have very different background because they look into the subject from all these different angles. Silvia will present the work being carried out within subtask B, which is titled Economic Strategies and Stakeholder Engagement. So Silvia, I'm looking forward to your presentation.
Thank you, Barbara. I will share my screen. Good. I hope you can now see my presentation.
Sure, we can.
Perfect. So, welcome everybody. What I will present today, as Barbara already mentioned, is related to the work we are conducting in subtask B in relation to the use of urban surfaces and the related benefits in solar neighborhood. So what we are looking at in subtask B, we are focusing actually on economic strategies and stakeholder engagement with the aim to foster the use of passive and active solar strategies, looking not only at the economic values, but also to added values and co-benefits that solar energy might arise. We have a broad range of activities, and in particular today we will look at some results and some work in progress in these three core activities which are related to the use of urban surfaces in solar neighborhoods. Why are we looking at surface uses in solar neighborhood, and why are we actually trying to define the most suitable surfaces uses in such urban areas? What we would like to achieve is having a broader focus. So we would like to consider all the surfaces available in our urban areas, which, as Barbara mentioned before, are a very relevant but limited resource. And we would like to aim to the use not only for solar energy production or the use of solar passive strategies, but also for the integration of a wider variety of solutions. Why this? Because actually the surfaces of our solar neighborhoods and our urban areas have an unprecedented exploitation potential. We have seen from studies in literature that actually roof allocate approximately 20 to 25% of the total urban surfaces, and the surface of the facades is almost double. So by using all these available surfaces, we might enhance not only the energy efficiency and the production of renewable energy in our solar neighborhood, but also the positive environmental impacts. So what we are focusing on, as I mentioned before, is not only active and passive solar energy systems, but a broader variety of solutions which we collected and discussed among the task expert in the subtask B. When we refer to active solar energy system, actually we include not only the energy system from the building envelope, which are the wider known solutions, but also energy system from the ground surfaces, such as PV pavements and other solar electric collectors for ground surfaces, and also energy system for urban features, such as the acoustic PV road barriers you can see in our picture. And when we refer to passive solar energy system, we just we focus on passive solar heating and passive solar cooling. But we also broaden our focus to other solutions, as I previously mentioned. So for example, we have a green solution, which include not only vegetation on ground, but also green building elements such as green roofs and green facades, and other innovative technological solutions such as these microalgae panels for the production of energy. We also have a water solution which might be used in solar neighborhood, from water bodies to evaporative techniques to reduce peaks of air temperature during summer, to water squares. We also included the potentialities to use urban agriculture, both ground-based, building integrated, or also other forms of urban agriculture, such as beekeeping in our solar neighborhoods. And last but not least, we also consider cool materials, so highly reflective and emissive materials, which allow to keep the surfaces of the building envelope cooler, and which are also strongly related to the solar radiation, and also other innovative solutions. We also consider, obviously, the presence in solar neighborhood of traditional uses and materials, which actually builds our urban areas, but also the potentialities for smart solutions. What then is what we then discussed in subtask B are the conflicts and synergies which may arise among surface uses. So the question we posed ourselves has been, can we integrate the solar active and passive systems with also other solutions in order to better exploit urban surfaces? What we did was to create a sort of matrix in which we analyzed conflicts and synergies among solar active energy systems and other solutions. One case is the one you can see in the picture on the right, a biosolar roof, which integrates PV systems with the green roof, which also acts as a cooling element for the panels, and so and helps in enhancing the energy efficiency. But there are also other solutions, such as multifunctional solar green facades and cool roof integrated PV. So just an example of what we would like to do in fostering the use of urban surfaces. This is the case studies of an industrial neighborhood in Bolzano we are analyzing in the context of task 63. And this is relevant because it covers a large portion of the city of Bolzano. And what we would like to propose through our activities in the task is a methodology for moving from the current configuration of the district, which actually integrate the common surface materials and some solar active systems, to a surface use pattern, so a configuration of the district which integrates also more innovative solution in which the use of solar active system is enhanced, and there are also other solutions such as green solution. how this might be done through several methods, so integrating on-site monitoring, the use of environmental tools, and also multi-criteria approaches. And what is then done, of course, the results are analyzed. Here you see some example of analysis with relation to some environmental parameters, so air temperature and human thermal comfort, but also the analysis of the solar potential and so on and so forth will be carried out. So what's coming next in relation to these activities in subtask B and in task 63? First of all, by the end of February, we will release our first deliverable, the deliver a report on surface uses in neighborhoods. Focus on how to define the most suitable uses, but also avoid conflicts and create synergies. So if you're interested in the topic, keep an eye open and on our website, and you will soon find our first deliverable. But we will also focus, as in the example I shown you, on the individuation of methods for the definition of the suitable urban surface uses in solar neighborhoods, based obviously on site-specific objectives. And we will also focus on the benefits, not only the financial ones, but also the environmental and the social ones, which then integrated use of urban surfaces might provide in solar neighborhood. And in relation to this, we are actually working also on the identification of the potential co-benefits related to the use of urban surfaces in solar neighborhood. What we highlighted in our discussion and work in the task in these 2 years is that actually urban surfaces are a key resource to tackle several issues related to urbanization and climate change. So they offer benefits not only related to the production of renewable energy, but also to other sustainability benefits, for example, the availability of rainwater and the food provision, but also they offer benefits in fostering climate resilience. So for example, they allow to improve the management of urban climate, to preserve habitats and biodiversity. They contribute to the management of stormwater and also to the amelioration of air quality. What has been the first step in understanding the relevance of these potential benefits in solar neighborhood? It has been a survey which aimed to identify priorities in the design and implementation of solar neighborhood. We actually asked to our participants to evaluate 55 urban challenges from 0, which means not at all relevant, to 10, which means extremely relevant. We've done and we are doing this in 2 phases. In 2020, we opened this survey just to the task 63 experts and we got 25 responses, while this year in 2021, we are diffusing this survey also among external experts and practitioners. And this activity is still ongoing, so you are really welcome to contribute to this. While we decided to open the survey from to external stakeholder, it has been because from the analysis of the responses we've got from the task 63 expert, we noticed that actually our point of view is quite limited. Many of us are engineer or architects, still have a very focused experience on design, urban planning, and also solar active and passive systems. And so some of the responses we've got on the relevance of these urban challenges might be influenced by our background. As I will just bring you some of the examples of the results from the survey carried out in 2020 among task 63 experts. One of the area we focused on is climate change. actually experts perceived as very relevant issues related to climate mitigation and climate adaptation, but consider less relevant issues related to water management and also flood management and increased urban ventilation, which of course in other cities and in other area of the world might be more relevant. Another field investigated by the survey are environmental aspects. Also in this case, we got some results which might sound surprising from you audience external to the task. For example, solar access and optimal use of daylight were among the challenges and benefits perceived by the expert as more relevant, but actually they some other challenges and benefits such as visual comfort and biodiversity preservation received a score, an insufficient score. So obviously, this is related to our focus. We are working on solar active and passive strategies, but this might obviously not reflect what is the external perception of what the solar neighborhood might provide. And that's why we are distributing the survey among external stakeholders and why we are also asking your inputs. Another aspect we analyze this, and we are analyzing is also resource management. In this case, the management of renewable energy and the provision of clean and local energy consumption were identified as the most relevant, while waste reduction and food security were less considered. If we move to social aspects, also in this case, we got some surprises. The presence of public spaces and an increased quality of life for health and well-being were highly considered by the experts. But, for example, acoustic or also gender equality received a very low score. We also analyzed economic aspects. Here, peer-to-peer trading of energy and prosumer-based business models are perceived as very relevant by the task experts, while real estate value increase and the increment of energy prices less. So, as I mentioned before, the survey is open to everyone and it will take approximately 10 minutes to complete it. The answer will be anonymous and then the results will reported in an aggregate way. So feel free to contribute to it. There is the QR code here available in the slide, and when the slide will be circulated, there also the link. And with this, I thank you for your attention, and I hope you will keep focusing and following our work also in the future and be interested in our future results. Thank you.
Thank you, Silvia. Very nice. Interesting results from this survey, I think, on understanding how the different factors play together, because there are, competing effects in urban planning. So we come now to our last speakers, which will be a tandem. They also chair the subtask C together, which is on solar planning tools. We have Martin de Boll from France. He is a researcher at the Logi laboratory. He's mechanical engineer by training, and his research focuses on applying thermal and fluid science on the deployment of solar energy in urban environment. And he is joined today by Juri Kandel, assistant professor at the Division of Energy and Building Design at Lund University in Sweden. He is an architect by training, and Juri's main research interests are on the integration of solar energy in cities and circular building designs. So they will join together to present this work, which is done in solar planning tools in subtask C. Yes, The floor is yours. Martin, you start.
Can you hear me?
Yes, we can hear you and see your screen.
Perfect. Okay. So thank you a lot. So maybe as you just saw, solar neighborhood have a very huge potential, and the use of solar energy is very important in a district and in neighborhood, but it's also very complex. It's complex because it has a wide, you can have a wide variety of use of solar energy and also of surfaces. And as you could have understood, it is crucial to use solar energy smartly for many different aspects, for the energy transition, to ensure thermal comfort, and also in the context of climate change. To ensure this good use of solar energy, we need tools, and this is all about the subtask 3. What are the tools, and how can we use tools and workflows to apply it to solar planning a neighborhood? The idea is here to bring some knowledge to support decision in this complex environment, and we focus here on active and solar potential, and active and passive solar potential. Just an illustration of the complexity could be seen here from an illustration of Emily nodes. Here you can see that in the planning of solar energy neighborhood, you have many different factors that appears, and one of them is the scale. Because if you take the urban scale or the building scale, you have many different things to address. The data is not the same, the quality of the data is not the same, and you have different layer of tools that you can use, and you also have different type of actors and users at each steps. So in what follows, we will show you some achievements we have been doing in the subtask C. One about gathering smart and relevant performance indicators, one about trying to gather workflow stories to identify current tools and best practice, and some comparisons of current tools.
Yes, thank you, Martin. Yeah, so one of the first things that we did within the task was to gather something that we called national common indicators. So they are basically key performance indicators that are very specific to the participating countries, and we gathered those common indicators that were both related to the active solar energy potential, meaning, for instance, the solar thermal potential or PV potential, but also on the passive solar energy potential. And here you see one of the tables that we found from looking at legislation in the participating countries. For instance, when it comes to direct solar access. So in some countries, the legislation state that, for instance, a bedroom should have at least 2 hours of direct solar access at a certain date. While other countries might say that, well, at another date, it's maybe 1 hour or 3 hours. And there are pretty big discrepancies between the countries, and even though they are at the same kind of latitude. When it comes to the active solar energy legislation, there are not many countries that actually prescribe when you are constructing new buildings that you have to install an active solar energy system, being it like PV panels or solar thermal panels. So it's kind of interesting to see the difference between the different countries. Can you do next, Martin? Yeah, so then we looked at what are the implications of those different common indicators. That's why we took 3 national common indicators to kind of showcase the implications of those common indicators. So we took a rather random courtyard building and then we simulated this courtyard building at different latitudes. So meaning we looked at the different solar conditions at the different latitudes, and then we applied the different national common indicators to this. And then you can see on the right hand side, for instance, this graph here, that those is the share of the courtyard facing facades that are not meeting the thresholds of the national common indicators. So of course, the higher on the latitude, the harder it is to reach those thresholds, and this you can see pretty well, I would say, in this graph. So and again, it kind of demonstrates the fact that even countries at the same latitude might have a very different approach to what solar access is and what level is considered to be a good solar access. Next, please, Marta. Then parallel, I would say, to gathering the national common indicators, we also were interested in how do key actors in the design process of solar neighborhoods use tools, and that's why we have something that we call the workflow stories, where we actually gathered this. Yes, thanks, Marta. So this is one example of a neighborhood which was evaluated by, in this case, a commercial consultancy company, where they looked at different performance indicators. For instance, how much of the facade reaches a certain threshold of direct solar access. So I don't know, could be 2 hours on somewhere in January, or what is the irradiation on all the surfaces. Those kind of things that they have worked on. But then what we were interested also was not only the indicators, the key performance indicators, but also which tools they have used to assess those key performance indicators. So for every of these workflow stories, we asked the people that wrote these workflow stories to provide input for the tools, but also output, and also describing the workflow. So different. Sometimes you need, since the urban planning is a rather difficult process, it might be that you have, as Martin already said, different data available with different quality. So it might be that you have to use different tools in order to kind of give answer to the performance of a neighborhood. Can you go next slide, please? Another example is this by White Architects in Sweden, where they are demonstrating like an in-house tool. So, for instance, architects within the company are using different 3D modeling environments, but they all want to kind of assess the performance of a neighborhood or a building. So what they did was here that they kind of developed a workflow that could be fed by different 3D modeling environments, but the outcome would still be the same performance indicator. Next, please. Well, here's another example of a advanced solar map where one of the task experts kind of developed this solar map where you can get more information about the conditions for your real estate property if you're interested in installing, for instance, a PV system or a solar thermal system. Yes, next, please, Madame. And here also, like, this is not very it's not very simple to do all these kinds of simulations, and you have to kind of find a way. Sometimes you even have to develop your own modules in order to get the result. So, and here's just an overview of some of the other workflow stories that we gathered from different companies or from academics, where people have used different tools to kind of to analyze the potential of solar neighborhood. Yes, Martin.
Okay, so I will finish with one last thing that we want to study with we carried within the task. So as Yuri just mentioned, there is a lot of different tools, and one thing we thought was to try to use a maximum of these tools doing the same task, what we call here a benchmark study. So for this study, we set up some rules. The rules are quite simple. We use two different districts, one which is like a grid district and the other one which is more random. It's happening in Geneva, and we provide it to experts. We provide them with the geometry, the location, as well as the weather data. So basically, we are supposed to have for everyone to have the same simulation condition, initial condition. Regarding the tools that we used, here you have a list on the left-hand side of the tools that we have been benchmarking. One thing that may be interesting here is that these tools were not, at the origin, they were not designed for the same purpose. Some of them were more designed to perform daylighting study, whereas other one were more about energy in cities, or even there is a solar map of Geneva that we just talked about. And there is also one beam and one model which is used for weather prediction in physics. Here you have an illustration of some results that we got. So I took the case of this district, and we focus on the central building here, the building 5. And what you can see are the distribution of the irradiance, of the hourly irradiance on each of the facade. So on the roof here, and here on the west, north, south, and east facade. One of the first thing which is very interesting is that even though we try to give the exact same initial condition to each of the tools, then we have as many different results as there are tools. So you can see that there are no two identical results in these plots. So this is one of the first very interesting point, because actually all these tools are quite, they are reliable, they have been validated, but you can see that even if they have all been validated, we still have some differences which are sometimes far too being neglectable. We can see that there is usually less variation when there is direct sunlight, for example, on the roof or on the south. We have variations that can reach up to 150 water per square meters. And also we don't have one tool which is constantly over or underestimating the predictions, the solar irradiation. Another way to analyze the data is to draw this kind of facade mapping. So here I went back on this homogeneous district, and this is the east facade at 10 and 11 a.m. So what you can see here is actually the distribution of the irradiance. When it's red, it means that there is a lot of a high value of irradiance, so usually it's direct sunlight, and when it's yellow, it means that it's a shaded part of the building. And you can see once again here that we have very different behavior, and we don't have two identical results within all our results. We have different behavior. Some predict a sharp distribution, such as in VMET and Quetzal, or some predict a smooth or some, let's say, fuzzy distribution, for example, in Deluxe or the Illuminae. And this is due to many different ways to model that I won't talk in detail here. So it could be due to the physical modeling, also to the way to handle the data and handle and how the workflow is built. So to finish, here we are the midterm of the task. And what we plan to do is a roadmap for the improvement of the workflows and the solar planning tools. So here we showed you some of the results we got, and all these results, all these first results and studies are here to set a state of the art, a status. Where are we now? What are the tools? What are the KPIs? what are the how do different tools perform compared to each other. Then in the second part of the task, we want to, from here, to have a vision of what we should do and to set different milestones in order to improve this workflow in the context of a solar neighborhood. Thank you for your attention.
Yes, thank you very much. Great input. So this last slide was on tools, which seems to be also a very important support measure for urban planners. So we are now at the Q&A session. Thank you to all the speakers. And I think we have some really tricky questions, but the first one I want to address to Maria, because one of our participants wants to have again a sort of, well, overall definition on solar neighborhood. So what is your definition for this solar neighborhood?
Well, yes, as I mentioned in my presentation, a neighborhood is really this group of buildings with different, could be different or the same type of buildings and uses. But solar neighborhood is, I would say, when you strategically use solar to achieve sustainability goals like zero emission or zero energy or plus energy neighborhoods and so on. So it's when you're really focused on developing different solar strategies, and it could be passive or active use of solar.
Okay. Thank you. And then, yeah, we have questions which were addressed to Caroline, but we said we will try to get an answer for them here. There's one, we were asked, what is the assumed load profile for the simulations? I think the person is asking whether the electricity which is here used in these simulations is typical for today, or is it already considering this future electrification simulation outcome where, you know, like heating and mobility will be also electrified and the electricity demand will increase overall?
Yes, maybe I will try to answer.
Yeah.
Well, it's not really defined yet exactly how we will do the work, but one way we have discussed is we have these, we maybe start with a neighborhood or existing neighborhoods, and we then try to improve them in different ways. And so we kind of have a base case or reference cases. And then we have more traditional load profiles, I would say. But then we want to look into the future of solar neighborhoods and how you can improve it to, yeah, so you can get very good ones. And in that case, you need to change the load profiles into future scenarios, I would say.
Okay. Does anybody of the other speakers want to add on this? Do you have experiences with that? Overall electricity consumption increases? No? Okay, then, well, there's another question that refers to maybe Maria or maybe Martin or Yuri as well, because you did international, well, approaches. How could you implement your proposed study in different regions, for example, rocky or mountainous regions? Maybe Maria, you can start on that, and maybe Martin can add.
Yes, I mean, if we when we define and describe different archetypes and to make analysis on and simulate, we of course need to take into account the surroundings. If it's mountains and things like that, not where I live, but then we need to describe that in the model, of course, to be everything that could have an impact and influence the performance of the neighborhood. We would need to include in the model.
Mm-hmm. Okay, particular mountain regions. Martin, have you ever looked into that? Or was it, you said you were talking about different irradiation levels?
Yeah, so actually Geneva is kind of in a mountainous region. It's not big mountains, but it's surrounded by mountains. So there is two things. One thing is when you predict solar energy, then you should take into account the mountainous region, the relief, because you have more complex shadings from this. This is one thing, but also one thing that should be aware of or focus on is that sometimes in mountainous region, you have a very specific climate, which is not very well represented by the weather station, because the weather station is maybe in an airport or in a and when you are up there, you have less clouds, you have more maybe irradiance, it depends if there's snow or not. So you have very specific conditions. And actually, so here we, the work that we set up, we use the exact same conditions, but maybe here we will have one tool that performs better than the other, but it doesn't mean, it means that this tool performs better in Geneva, but it doesn't mean that this tool will perform better in mountainous region or somewhere else, because physical hypotheses can be different in different places. So this is something that we should be careful with, to not have like conclusions, drastic conclusion for every product, and be aware of different problems that can issue.
Actually, another question regarding performance of tools, or well, how they are used, maybe to Martin. Somebody asked, do you address the usefulness of renewables in real time if you simulate, or do you address net zero on a yearly basis? So that means if you produce in summer and you use in winter, it's still net zero.
I guess this is more linked maybe to, we haven't, in STC yet, we haven't coupled the production and the consumption of the buildings, except through indicators, but the way the indicators are calculated is dependent on the on countries or on the methodology. So maybe Caroline will have a better answer than I do. I don't know, Yuri, I think do we have indicators on the self-consumption?
I think, I mean, it depends on the purpose and like on the case study. So in the workflow stories, what we tried to show is what some of real world examples where there were clients normally, and there were consultants working with tools in order to kind of achieve a high standard for instance, a building or for a neighborhood. So, and if the goal was to achieve, for instance, a net zero energy building, but on an hourly basis rather than on an annual basis, then that was done. But I would say when it comes to legislation, it's often that they look at the annual time resolution rather than the hourly time resolution. But I would say a lot of tools are actually able to address the hourly time resolution.
Okay, thank you. Yeah, Sylvia, I think we also have some questions for you. There's this question you mentioned, cooling materials, which could be put on the facade to cool buildings or the facade. How does this work?
Well, there are different solutions, obviously, which are being, some are still being studied, some are kind of mainstream solution. One of the solution I mentioned in the presentation are cool materials, how these materials work and why we somehow relate them also to solar energy. It is because these materials are characterized by high solar reflectivity and high infrared emissivity. So in such characteristics allow to decrease the surface temperature of the facades and then also the solar gain in the interior of the buildings. This is so to say the most common solution, but actually also we look at green solution. Green facades have some sort of effect on cooling the surfaces on the building where they are applied. And if we look at more technological solution, also cool materials are being coupled, for example, with phase change materials or other technologies to provide further insulation and cooling.
Okay, thank you. And another question says, what innovations are available and possible for foresighting for integrated solar agriculture, especially in urban farming initiatives?
Well, actually, also in this case, there are some already existing and on the market solution and some which are still being developed. If we look at the ground surfaces, so at so to say, common urban agriculture or to urban farms on rooftops, actually there are different possibilities. On one side, the use of solar active systems, so PV or solar thermal panels, has shading elements. In this case, there might arise some competition among obviously the production of renewable energy and the agricultural production, but there are also some studies which have shown that this integration allow the preservation of some habitats and also the increase of plant diversity. Another solution is the integration of solar active systems on the greenhouses, in particular thin film or semi-transparent photovoltaics are solutions which can become part of the exterior of greenhouses. And if we look at more innovative solutions, there are some studies in particular in Singapore on productive facades. So these are elements which integrate PV panels and vertical farming solution, and they are conceived as modular systems that might be substituted to some common components of the building envelope.
Okay, interesting. Well, you have examples from all around the world. Very nice. Yeah, we have another technical question to both the tool users, Martin and Yuri. What format of weather files are used in the simulations? Was it the one from Energy Plus database?
Yes, it was the one from Energy Plus. We just one difference is that we modified it. We keep the same format, but we modified it because we had 10 tools, and some tools were able to perform annual simulation, so modeling every day, and some tools were too slow to model a whole year, so they could model just 1 or 2 days. So we define what's it called it's an average day, which represents best 1 month. So we took 1 day of August and 1 of February, and this day is a day that represents best the month of August and February, and we just use this day in an EPW format, so the format of Energy Plus.
Okay. Well, another question which might be also linked to your work rather, somebody wants to know, do you also plan or analyze, optimize the issue of energy storage and dispatching in the neighborhood, for example, considering heat and electricity networks?
I would say that I don't know, Maria, if you also have something to say about it, but we kind of said that of course, like grid interaction is an important issue, but when we haven't seen that much yet when it comes to tools, like how to analyze this grid interaction, for instance, this kind of thermal storage. So there are often very specific tools that can do this, rather than, and they're also on a very small scale with a very high level of detail, meaning that you not always, I'm not saying this, but I'm trying to, so we are very much looking into some kind of first stage decision making, where of course grid interaction, for instance, could be very interesting, but the focus is not there, at least for now. and it has not been much in the task either, I would say.
In your task. So maybe may I ask how far, well, are these tools that you listed already known or used in city administrations? Or is this is it spread already? Are these tools known?
Well, I would say that we are, if I generalize, then which is always a bit tricky, but I would say that a lot of urban planners, as for instance at the municipal level, they don't have a lot of knowledge about how to use tools. So they would rather have access to someone who's performing the simulations for them, but so kind of looping back, like giving feedback on their design rather than actually doing the simulations themselves. So I mean, the tools are out there, but it's just that finding the way to practice, for instance, in the urban planning daily work, they are not, I would say, they are not using this kind of tools, but they can, but they would really like to see this kind of feedback to their plans, but they just don't have either the access or the knowledge to kind of use these tools because they have to consider so many other things in the urban planning process that solar access or active solar energy potential is just one of them, just one on the list.
Okay. Well, because we have this interest. Yeah. Okay. Go ahead.
I can add because one thing about well, self-consumption is also and this idea of storage energy and exchange of energy is that you need to be able to predict the solar energy that will be produced at very wide scale, at a city scale, which means that you have a very huge area of a city, of a country, and you need also because solar energy can change from 0 to 100 or to 1,000 in 1 second. So you need a very, very fine temporal scale, which means that you need tools which are very performant, either spatially and which we cannot really achieve now at big scale. We can do it at small scale, as a building, maybe a district, but not so much. And this is actually scientific also deadlock is to be able to simulate it in a smart way so that we can simulate large scale, to simulate all this exchange, the energy production, the energy needs, and the energy storage. So this is something also, that is why also in current tools, it does not really appear because there is not one satisfying solution yet.
Okay. There's a question to Maria as well. And somebody is asking, does the task also include the user perspective, like policy measures or engagement of citizens? For example, how city governments can work with policy or incentives to increase solar energy implementation?
Yes, it is citizen involvement. This is part of the subtask B, we could say, from Sylvia. So maybe you can comment on that further.
Yes, it's something obviously really relevant for the diffusion of solar active and passive systems, and is something we will and we started looking at in subtask B. So in particular, what we are trying to understand is which are the best ways to involve citizens and other stakeholders also in to foster the diffusion of solar active and passive systems. We are taking as example some projects, in particular the European projects in which we are also involved, for understanding how, for example, targeted interviews, workshops and presentations might contribute in also increasing the knowledge base on such renewable energy systems and have an impact also on their diffusion.
Okay, thank you. Yeah, maybe last question, a challenging one as well. We have Peter Wang asking us, maybe to all the speakers, do you have the municipal government laws or regulations to support your projects, or are all your projects like scattered experiences or niche showcases? So maybe we go to Maria shortly and let the others also comment on that. We have a few minutes left.
I mean, the case studies we have, it differs from country to country, I guess, because how you cooperate with municipalities and others. So it's not some general strategy we have, but it's more where things happen or that we have some connections and there is a development ongoing or in planning, and we have connections, and we try to work together and support the planners, and then we can get some knowledge back and feedback and test our tools and methods, and so it's a win-win situation. But it's more on, it's not any specific strategy of which cases, but maybe someone else has.
I think maybe the question also wanted to address the fact whether like frame conditions like this discussion in Europe about PETs, like positive energy districts and stuff like that, will sort of form a policy framework that makes your life easier in the future because everybody is more aware. I think maybe the question was in this direction. So maybe Sylvia, Martin, Yuri, you see any effects on this? Is the awareness increasing? Do you receive more requests? Is there a higher interest?
I think, I mean, yes. One thing that I could say is that especially when it comes to solar access, I would say within the European Union, they are now kind of streamlining different like national legislation. For instance, when it comes to solar access on facades or windows, you need to have, well, it's still a kind of an advice, but recommendations, but the member state countries, they have to kind of adapt their legislation towards this European norm. So you kind of see that even though the thresholds that are used within this norm are different from country to country, the way to calculate things or the way to analyze, like assess the, for instance, solar access, they are all like streamlined. So it's much easier to kind of adapt to that. And I think that local governments then have to kind of think that, okay, how do we make sure that the neighborhoods that we are designing are in such a way that real estate developers or architects or whoever that is involved are able to meet the thresholds, and it's their task to kind of make sure that they do this. So I would say if you already from the European Union level, it goes down to national legislation towards the municipal legislation. So it's this whole stretch that we are kind of, it goes from the very large scale to very smaller scale, like the municipal level.
So really you see some movement trickling down. Any additional comments? But we are almost at the end from the other two speakers.
Maybe to finish with what Yuri said about municipality, and we worked in a project with building a solar map for a big territory with many municipalities, and now we have a lot of municipality asking they want to have solar energy, but the thing that there are no technical or engineer in the municipality, and they don't know where to start. They don't know anything about what to do. But this is something that we observed a lot, and this is something to think about and to develop, which are tools for people that also doesn't know anything at municipal level, because there is a lot of willing to go in that direction, which is very good and should be encouraged.
Yeah, perfect. I thank all the speakers very much for this very interesting presentations, engaged answers to the many questions. To all the participants, watch out on the Task 63 website. I think there are a lot of interesting reports coming up in the next 1.5 to 2 years. You have the website IEA-SHC.org and you look for Task 63. So I will hand over to Arabella, our ISIS host, with wishing you all a nice afternoon or the rest of the day and thanking you all for your participation. Bye-bye.
Yes, thank you, Bärbel, and thank you to all the speakers for this great webinar today. I think we received really good questions and I think important conversations for sure. There are a few final announcements I want to make before I release everybody back into their busy days. And one is, it's always an important one. Yes, there is a webinar recording. It's just recording as we speak. And it's going to be available both on the ISIS homepage as well as the IEA SHC Solar Academy. Please give us a few days for that. It needs to be edited, and then it's going to be up there for you to come back. And you will also be able to see the presentations which have been submitted by the presenters. For our ISIS members, remember you already have unlimited access to all past ISIS webinars, including the IEA SHC ones in the ISIS membership area. So that's always worth checking out. And then there's one new thing coming up because after the Congress is before the Congress here at ISIS, we are having Eurosun 2022 coming up next year in September. And this is especially well fitting for this webinar today because it's an ISIS and IEA SHC International Conference on solar energy for buildings and industry. So I'm sure that our presenters today also could be interested in that particular conference. Yeah, so for everybody who's interested, you see the website address down below. It's eurosun2020.org. And we are going to issue the call for papers and call for participation in early 2022. So use the Christmas time wisely and get prepared. And you're going to see that call coming out in early 2022. Yeah, and with that, a big thank you from my side as well. If you want to reach out to ISIS, you can always do so at public.relations@isis.org if you have any questions, comments about this webinar or any other ISIS events. And obviously, you can always find us on all the social media channels. And there's a tiny survey coming your way after this webinar. So if you want to complete that, that would be awesome, because then we can improve the webinars even more. Yeah, I think with that, thank you everybody for joining us today. Take care, and yeah, let's talk again soon. Bye everybody.